For these two examples, really we can just use our Algebra 2 skills to find asymptotes. If a question says find asymptotes and you remember all of the rules about degrees and the exponents and stuff, go ahead and use those, okay? And remember, asymptotes, we do need to have an equation for, not just a value. All right, so for this first one, for vertical asymptotes, we need to check the denominator and see where the denominator equals 0. X squared plus 4 does not factor as x plus 2 times x minus 2 because we have a sum in the middle, okay? So, switch this here. So there are no vertical asymptotes. Let's make a note of that. Okay, for horizontal asymptotes, is where we consider the degree. And because the degree in the denominator is greater than the degree of the numerator, we know that our horizontal asymptote has to occur at y equals 0. Okay, now, real quick, I want to show you how you would do this with limits if you wanted to. Okay, so to check for a horizontal asymptote with a limit, then what we would do is we would ask, what is the limit as x approaches, and you could put plus or minus infinity. It doesn't matter. I'm just going to use positive infinity consistently here. Okay, so limit as x approaches infinity of x over x squared plus 4. Okay, now if I plug infinity in, I'm going to have infinity over infinity squared plus 4, which is infinity over infinity, and as we saw before with the arithmetic, we can't do infinity over infinity as itself. So we need to do some kind of algebraic manipulation, all right? And this one's going to be a little bit new, but what we're going to do is we are going to divide the entire fraction, okay, by, switch colors here, by x to some power, okay, in such a way that we have that we choose the highest degree power from the denominator, okay? Sorry, I was a little convoluted when I said it. I got distracted changing the color. Okay, so in other words, since I have an x squared in the denominator, I'm going to divide everything on the top and bottom by x squared, okay? So divided by x squared, divided by x squared, divided by x squared. And as long as I do that with every single term, then algebraically, I'm not changing my expression or my function. So this gives me the limit as x approaches infinity of, and then I have 1 over x in the numerator, and in my denominator, I have 1 plus 4 over x squared. And you may be saying, okay, but now you have complex fractions, and usually we try and get rid of those. Normally, yes, when we're simplifying, but in this case, I'm limited on what operations I can do with infinity, and this allows me to evaluate, okay? Because now, if I plug in infinity, okay, I have 1 over infinity, which I know goes to 0, okay, over 1 plus 4 over infinity squared, which again goes to 0, and that's 0 over 1, which is just 0. Okay, so I still get y, and I need y equals, but I still get y equals 0, but this is just using another process. So if you don't remember the Algebra 2 rules with degrees of numerator and denominator or anything like that, or it's a little bit more complex, then you can always use this process of dividing everything by the highest degree from the denominator, okay? And we'll see at least one more example of that here in a minute. All right, for this next one, okay, for this next one we have, oh, sorry, everything shifted. Okay, we have x squared minus 2x plus 4 over x minus 1, okay? So first of all, looking at our denominator, we do have a factor that can be set equal to 0. So x minus 1, if we set that equal to 0, we get x equals 1, meaning that there is a vertical asymptote at x equals 1. Okay, now we do need to check to see if x minus 1 is a factor of the numerator. We're going to see here that it's not because that can't be factored. Okay, but definitely make sure that you're checking because otherwise you have a hole, not an asymptote. All right, and then horizontal asymptotes, because the degree on top is higher than the degree on the bottom, we do not have any horizontal asymptotes. All right, and again, I'll show you how to do this with limits. So limit as x, don't skip ahead yet because there's another one, but limit as x approaches infinity of x squared minus 2x plus 4 over x minus 1. So here, if we divide everything by x to the first, which is the degree from the denominator, we get the limit as x approaches infinity of x minus 2 plus 4 over x all over 1 minus 1 over x, okay? When I plug in infinity, I have infinity minus 2 plus 0, which is still infinity, divided by 1 minus 0, and infinity divided by 1 is infinity. Because this is not a constant, that tells me there is no vertical asymptote, okay? So if a question says find a vertical asymptote and you use limits, don't say infinity, okay? Say no, I'm sorry, horizontal, not vertical. Back up, horizontal. Don't say that your horizontal asymptote is infinity, okay? Because it is not. However, there is one other asymptote for this particular function because the degree on the top is exactly 1 higher than the degree on the bottom. So that means that we have a slant, or like the book calls an oblique asymptote. Okay, so to find that, we are going to divide. Okay, and because we have a quadratic divided by a linear, I'm just going to use synthetic division because that is more efficient. Google it if you don't remember how to do it, or you can do long division if you remember that one better. It's not a very complicated one no matter what. Okay, so we drop the 1 down. 1 times 1 is 1. Negative 2 plus 1 is negative 1. Now, if you remember from Algebra 2, finding your asymptotes, we would stop right here and not care about the remainder. I'm going to finish this and explain why we don't care. So negative 1 times 1 is negative 1, so that's a 3. Okay, so when we divide this polynomial by this polynomial, we get y equals, this is your linear term, this is your constant, this is your remainder, so we get y equals x minus 1 plus 3 over x minus 1. Okay, so these two things are equivalent. Okay, we've just written them differently. It's kind of like we reduced a fraction, it was just complicated with variables. Because of our definition for horizontal asymptote, okay, which is limit at infinity, remember that if we evaluate the limit as this goes to, I mean, yes, we're going to get infinity, but if we evaluate a limit at infinity, what does this piece right here give us? 0. Okay, so the reason we don't care about the remainder is because when x is approaching infinity, this drops off. So our slant asymptote, or our oblique asymptote, is y equals just x minus 1. Okay, and if you think about what a slant asymptote looks like, so let me just give you a quick example. So y equals x minus 1, that's going to be like this. Y equals x minus 1. Okay, so this function, and then vertical at x minus 1, this function, wherever it is going to curve into these. I believe it's here and here, okay? It's going to curve into those asymptotes. Here, we are still approaching infinity as x approaches infinity, but the further we get, the smaller and smaller this remainder piece gets, and that's why the curve gets closer and closer to the line y equals x minus 1. Okay, so hopefully if when you learned asymptotes there were some holes in the logic, or some holes in like things that just didn't quite make sense, hopefully thinking about these from a limit perspective will help fill in those holes, because I really want you to understand the concepts, not just a procedure. Okay. All right, so in the 1.1 and 1.3 notes, we had the strategies for evaluating limits analytically. Okay, remember we first tried direct substitution. If we get some real number, a constant, or if we get something that doesn't exist, all right, or plus or minus infinity, then we know that we're done. Okay, like we can't have a limit at infinity, especially like y equals x squared as x approaches infinity is just infinity. Okay, however, a lot of the times we're going to have an indeterminate value, or undetermined, same thing. So like 0 over 0, infinity over infinity, that kind of thing. Okay, so We can try some algebraic reducing or factoring. We can try rationalizing or multiplying by conjugate. If we have infinity over infinity, this one is new, we divide by the highest degree term from the denominator, like we did over on this side, okay? And then we also have that trig theorem of sine x over x as x approaches 0. So if applicable, we could use that, okay? And then if none of those work, then we want to plug in the close values, or, you know, consider it graphically instead, okay? And as I'm doing this, I'm remembering that in the last video, I did not answer this last question, so backing up real quick. If we have a constant divided by 0, no, we can't divide by 0, but if this is one-sided, if a one-sided limit, okay, then this approaches either positive or negative infinity, okay? So like in the case of 1 over x, as we got really close to 0, so 1 divided by 0, from the right it approached positive infinity, and from the left it approached negative infinity. Okay, sorry, I realized that I didn't finish that in the last video. Okay, back down here, 2 more examples to try. If you want to pause it and try them on your own, that's fine. So for this first one, limit as x approaches negative infinity of x squared plus 3 over 2x squared minus x. Here, because direct substitution would give us infinity over infinity, we're going to try option C here, where we divide by the highest degree from the denominator, which is x squared. So dividing everything by x squared, okay, gives us, keeping my limit notation because I still have x's, oh, negative infinity, not positive. I have 1 plus 3 over x squared all over 2 minus 1 over x. Plugging in negative infinity, I get 1 plus something that approaches 0 over 2 minus something that approaches 0, which is 1 over 2. Okay. Now, if we had recognized that a limit at infinity is the same as a horizontal asymptote, we could have used our algebra 2 rules to see that the leading coefficients of 1 over 2 are the horizontal asymptote because the degrees are the same. But again, it doesn't matter which way you approach it, okay? And then for this last one, limit as x approaches infinity of sine x over x. This one, really, I just threw this in here to point out that it is not equal to 1. And the reason is because this is not 0. Okay, so even if you see the sine x over x form, or its reciprocal like x over sine x, you cannot automatically just say, oh yeah, well the limit is 1, or it equals 1, even worse, because we might not be approaching 0. This is just like the one from the 1.3 notes, the example towards the end where we did cosine. Remember that sine is something that oscillates between negative and positive 1, and then as x approaches infinity, well, that's our denominator. Any number in between negative 1 and positive 1, so any constant, okay, even though it's a changing constant, it is limited within this range. Any constant divided by infinity approaches, I should use an arrow, approaches 0.